Welcome back, students. Let's resume. In the previous video, we talked about the sum and difference identities of sine, cosine, and tangent. Here we have sums only. Now we have differences as well. We also explore the relationship between sum and difference. In sum identity, which is standard, plus is changed to minus, and accordingly, this plus now became minus. The same here. This plus became minus, and consequently this minus changed to plus. For tangent, we see the same kind of sign change here. Sign changes in the left hand side, consequently we have the sign change in the right hand side. That way you can just memorize the formula for sum, and you can easily deduce the formula for difference. That way you can just memorize a little bit smaller number of formulas, and that's going to make your study more effective. Now, we talked about finding out precise trigonometric values using the sum and difference identities. And the typical case was when the angle was given as k pi over 12. 5 pi over 12 here, 1 pi over 12 here, negative 7 pi over 12 there. Of course, there are other angles too, but in any case, k pi over 12. How do we handle those? The key is to decompose the given angle in terms of two basic angles. Pi over 6 is basic, pi over 4 is basic too. So add them up, we end up with 5 pi over 12. This decomposition is not unique, but in this case, we end up with this kind of sum identity, and plugging all those values in from trigonometric table, something like that. In the end, we have the answer. This kind of answer, by the way, is not unique. Excuse me, what did I say? The answer is unique. The decomposition is not unique. The answer is, of course. For example, you can decompose it like this if you want to. This is what I forgot to mention. And consequently, this is, let's see, 3 pi over 4. And this is minus pi over 3. And then, of course, you can apply the difference formula for sine, and which is sine of alpha cosine of beta minus cosine of alpha times sine of beta. Plug in all those values from the trig table here, and then simplify. In the end, you should have the same answer, because answer should be unique, even though decomposition may not be. That's one thing I forgot last time about, emphasizing the non-uniqueness of decomposition. It doesn't matter in the end, because you should have the same answer in the end. We went through sine, cosine, and tangent. Okay, those elementary examples are done. Let's move on to a little bit harder example like this. Let's find out precise values of something like this. Now, this is exceptionally easy type of problem. Why? Because we know precisely what is arcsine of 1/2 and what is arctangent of 1. What is arcsine of 1/2? Is pi over 6. What is arctangent of 1? Is pi over 4. Consequently, all you have to do is to apply the sum identity for cosine, and we are through. Well, here it is. Apply the sum identity for cosine with these basic angles, pi over 6 and pi over 4, and you can look up the trig diagram, and then get all those values in, do the computation. You're supposed to get the precise answer. And no surprise here, we have square root of 6, square root of 2, and denominator 4. So just as expected. Okay, let's move on to the next type of problem, but this is different. The fundamental difference here is that we don't know precisely what arc cosine of 2/3 is, and we don't know what is arc cotangent of 3/2. We don't know that. In this case, what do? Well, we cannot use calculator, because if you use calculator and get approximate values, then we will not be able to find out the precise value. A calculator can help you guessing, but the problem explicitly said find out the precise value, which means not only the answer but also the process must be precise. Calculator will not be helpful. This is what you have to do. Name alpha as arc cosine of 2/3 and beta as arc cotangent of 3/2. And then consequently, you're going to get something like this. Cosine of alpha is 2/3 and cotangent of beta is 3/2. Please note the color coding so that you don't get confused. Blue condition, alpha is arc cosine of 2/3, gives you cosine of alpha is 2/3. And the red condition, beta is arc cotangent of 3/2, gives you cotangent of beta is 3/2. Now, how do they help us? Well, calculators or any other means to find out what alpha is or what beta is precisely, well, that kind of direction will not help you because it's impossible. But it is possible to find out the other trig values of alpha and beta precisely if you use pictures. Cosine of alpha is 2/3. Now, what is the definition of cosine in a triangle? It's adjacent over hypotenuse. So what we do, we have 2/3, so we draw a right triangle with adjacent 2 and hypotenuse 3. That's what we do, kind of like this. Please take a look at this blue triangle. Adjacent 2, hypotenuse 3, so cosine of alpha is 2/3, we get that. And also, we can easily find out the opposite. Opposite is square root of 5. We can do that from Pythagorean theorem. Let's look at the red triangle. Red triangle explains, well, this one, cotangent of beta is 3/2. Cotangent is adjacent over opposite. So we draw a triangle with adjacent 3 and opposite 2. How about the hypotenuse? We can find out precisely from Pythagorean theorem. We end up with square root of 13. The detail is left to the students. It's so simple. So from these pictures, we can find out sine of alpha, cosine of alpha, sine of beta, and cosine of beta precisely. How about sine of alpha? It's opposite over hypotenuse, so it should be square root of 5 over 3. And for example, what is cosine of alpha? That's 2/3. Let's look at the red triangle. What is cosine of beta? It's adjacent over hypotenuse, so 3 over square root of 13. How about sine of beta? It's opposite over hypotenuse. We have 2 over square root of 13. And a little bit of computation yields this kind of value, 3 square root of 5 plus 4 over 3 square root of 13. You can simplify if you want to, but this is precise answer that I'm looking for. Now let's move on to other kind of problems. Let me see. Okay, proving an identity using the sum and difference identity. Left hand side is tangent of theta plus pi over 4. So you can use the sum identity for tangent, it looks like. Oops, excuse me, wrong section. Here we go. Sum identity for tangent. So if you use theta in place of alpha and pi over 4 in place of beta in this formula, well, you're going to get a solution. Tangent of pi over 4 is going to be 1, so okay, I'll stop here. I mean, the answer key is hidden here, but it's so simple, then I'm going to leave those to students. Let's see, is there any other problem that I have to work on? Let's go over to these difference quotient problems. And this kind of problem is important in calculus. So let's talk about it. At this moment, you may not have a good motivation why we are doing this, but in calculus, believe me, this thing will come back and haunt you. So let's talk about it. Sine of x is given as, f of x is given as sine of x, and we want to find out this quantity, f of x plus h minus f of x over h. This quantity, by the way, is called difference quotient, or Newton quotient, named after Isaac Newton, the same person who studied and discovered calculus, among other things. Okay, let's go ahead and do the computation of the left-hand side. What is f of x plus h here? Excuse me, this notebook is a little bit problematic, so let's make a little bit of change before resuming our discussion. Okay, that's an improvement. So this is what we want to calculate. F of x plus h minus f of x over h. Denominator is of course h, so that's h. And what is f of x? That's sine of x, so that's easy. Now, what is f of x plus h? It's just a substitution. The definition is here, and we are replacing x by x plus h. So you have to replace this x by x plus h. Consequently, what we have is sine of x plus h. Let me expand the font a little bit further. Hopefully you can see things a little bit better here. Okay, so sine of x plus h is f of x plus h. Now, we know what sine of x plus h is because we know the sum formula for sine. So let's go ahead and do that. Sine of x cosine of h plus cosine of x times sine of h. Sum formula for sine. And then what we do now, let's look at the conclusion here. We have sine of x times something, cosine of x times something, and those somethings do not have any x in there, those are h. So what I'd like to do here in this mixed up state is to get all the terms related to sine of x in one side, everything related to cosine of x on the other side, and then consider them separately. This one has sine of x, and that one also has sine of x. So let's do it like this. Change the order. Like this. So this sine of x and the sine of x part stay close together, and then what we are going to do next, it'll be to factor sine of x out. This part is cosine of x, so move to the right. Okay, factoring sine of x out, we have sine of x times cosine of h minus 1, and the second term is all set. And then what do we do? Well, we just decompose the numerator. Denominator is h, so just decompose, and sine of x out, we have cosine of h minus 1 over h, and we have sine of h over h. It'll turn out that cosine of h minus 1 over h will get very, very, very close to 0 when h is extremely small. We call those kind of phenomena limit. So limit of this quantity will become 0. Consequently, this entire part will drop out. 0 times something, so it'll become 0 in the end. And the sine of h over h, okay, we can explain it at this course, but in calculus we will. Sine of h over h will get very, very, very close to 1 when h is very, very small. So what do you get? This is 1 times cosine of x. So this whole thing will approach cosine of x. And that's the kind of computation they do in calculus. Of course, that very, very close to something, something, something part is not part of pre-calculus, not part of trigonometry, so you don't have to worry too much about that. But as for this computation, that's important, especially considering that everybody who is sitting in this class is sitting here because he or she wants to take calculus, preferably in the very next semester. So this discussion was worth it, I think.